Okay, can you see that picture?
Yes, sir.
Yes, Dr. Julian.
Yes, sir.
Yes,
Yes,
Dr.
Julian.
Very good, very good. Let me just change a couple of things here. Right. Okay, so I'm going to talk a little about microgravity, which is quite an interesting and a bit of a strange topic. But so first of all, I'm going to tell you what gravity is, so then we can talk about microgravity. So let's start with gravity. And the first person to really get to grips with gravity was this guy here. He's called Isaac Newton, and he lived in about 1660, so about 400 years ago, basically. And he came up with, well, he didn't come up with the idea of gravity, that things fall to the earth. Everybody knew that, I guess, from many, many years. But he came up with the idea that there was some physics equations that govern this. So he came up with the idea of exactly how do things fall to the earth and what stops them falling to earth and all things like that. He lived about 30 miles away from where I'm talking from you now, in a place called Woolsthorpe, which is out in the country here in England. And he did this work, say in about 1600 and something. And at the time there was a big plague all around Europe, carried by rats, and so everybody was, if you were in a big congregation, a bit like coronavirus, I guess, but if you were in a big city, then your chance of getting plague was quite high. So everybody sort of went out into the country, into farms and places like that, to try and avoid getting the plague. And he went back to his farm, which is, I say, it's about 30 miles away from here, and did some of his best work all on his own, with his parents' farm, just sitting there thinking about things, and came up with this idea that gravity is an attractive force that pulls things towards you. So here you can see him sitting under a tree, and apparently, we don't know whether this is true, but an apple fell down from the tree, and in some stories it hit him on the head, or maybe he just watched it, but he wondered. This got him thinking, well, why does the apple fall down to earth, and what is the reason behind that, and is that the same thing that keeps the moon from getting away from the earth? And he started to think all about these sorts of things, and this is the ideas he came up with. And you can actually go to this place called Woolsthorpe Manor, which I say is about 30 miles away. I've been 2 or 3 times, and you can actually see not the original apple tree, because that died, but they when it died, they took an apple from that tree and planted one of the seeds and grew another tree. And you can actually go and see this tree that is a sort of child of the tree that he was sitting under. Okay, now the next bit is a bit scary because it's a physics formula, and you really don't have to understand too much about it, but I thought I'd introduce it. So here it is. Yeah, it perhaps looks a bit scary, and maybe you've not done any formulas or anything like that at this stage, but it does let us understand a little bit about gravity. So let me just talk you through this. So this F here, this is the force of gravity. This is how much things are attracted by gravity. We'll come back to that. G is just a big constant. We don't need to worry about that. That's just a number, and the number is always the same. Then there's 2 M's. These are 2 masses. So if you've got like an apple in one hand and an apple in another hand, they both have a weight or a mass, and so they have gravity between them. These 2 apples are actually trying to pull each other towards each other. But gravity is a really, really, really weak force. It's incredibly amazing how weak it is. So you can't feel the force between those 2 apples trying to pull each other together, because it's really so weak. So you need something really, really, really heavy to actually pull anything together. So we're all standing on the Earth, and that is really, really heavy, and we are getting quite a weak force pulling us down onto the Earth. So that is what we feel as gravity. So in this equation, one of those masses is the mass of the Earth, and the other mass is probably the mass of you, because that's how you feel it. But as I said, gravity is a really weak force. I'm sure you can all jump up, and you can jump up a few feet or centimeters, and you are fighting then against the force of gravity of all that mass of the Earth trying to pull you down. So it's a really weak force. You've got tons and tons and tons of stuff beneath you, all trying to pull you down, but your muscles can jump you up against the force of gravity. And the other thing that is important, so this is, if this picture was two apples, this M1 was one apple and M2, this is the force between the two. And it's also dependent on how far apart they are. So if you pull the apples further apart, the force gets weaker. And if you put them closer together, the force gets stronger. But as I say, it's a very weak force, so it doesn't change very much. And it's actually very, very difficult to measure this force due to gravity on the Earth, because it's just so weak. There are a lot of other forces that outweigh it. So if we use that and we're standing on the Earth like this, you can actually work out just from this equation how heavy you would be. And obviously you can do that, but you can also just use a pair of scales to weigh out how heavy you are. Now, what can change? So you could walk around the Earth and nothing much would change. You would still be as heavy as you were. The Earth would still be as heavy as it was. And your distance, this distance here from the center of the Earth, would be about the same. You could walk around the Earth and you wouldn't really feel any difference in the gravity, because it would be much the same. The distance from the center of the Earth, several thousand kilometers, would not really make any difference. If you went up a hill or down a hill, it really wouldn't make very much difference. So everybody feels the same amount of gravity really on the Earth, no matter where you are. But if you go to a different planet, then that does change things, because now you're not looking at the mass of the Earth, you're looking at the mass of the planet you're on. And here I've got a chart of various places you could go and stand on and how much you would weigh. So if you weighed 100 pounds on the Earth, or 45 kilograms, then you'd weigh something different on some of the other planets. If you went to the moon, for instance, you'd only weigh 17 pounds or 8 kilograms. So on the moon, you can jump really, really high because you are on a much smaller body and it has much less gravity. On Mercury is a bit bigger than the moon. It's a bit more. It's almost the same on Venus, because Venus is almost the same size as the Earth. Mars is quite a bit smaller, so it's again quite smaller. Jupiter is much, much bigger than the Earth, but it's also so it's much heavier, but it's also much larger. So you are further away from the center of the planet on Jupiter. So you weigh quite a bit more on Jupiter, but perhaps not as much as you might think. And it's the same on all the various other planets. You can calculate using that formula that I showed you, just by putting a few numbers in that, exactly how much you would weigh on all these planets. So that's what we've done with these cases. Now, as I said, you could go right to the very top of a mountain and stand on the mountain, and you would feel a bit less gravity, but not very much. If you went to the top of Mount Everest, the tallest mountain on Earth, you would feel maybe sort of a tiny bit less gravity, but really nothing you would notice. If you fell over on the top of Mount Everest, it would hurt just as much as if you fell over on the ground. So this is where we move to microgravity. So what is microgravity? So the further you get away from the Earth, because of the gravity is affected by distance between the two things, you would feel less and less gravity. So at the top of the mountain, you feel a little less, but once you get into space, so here are some astronauts on the International Space Station, they feel a bit less gravity, but really not very much. It's about 90% of that. So they would if they weighed 100 kilograms, they would weigh 90 kilograms on the International Space Station, just by the effect of gravity. But there is something else going on here which makes them a little different from that, and they really don't feel the sense of gravity, but that is a different effect, and this is what I'm going to talk about from gravity to microgravity. So what they're really feeling is the effect of falling. So they are actually falling around the Earth, but all the time, and that's a bit of a difficult thing to gather. So here's a little experiment that you can do in your head, because you can't do it in real life because it would be kind of dangerous. But here we have the Earth, and we put a big cannon on the top, on the North Pole, and this is going to fire a cannonball. And so you put the cannonball into the cannon, and you put some gunpowder into it, and you light the fuse, and it fires the cannonball. Now, depends how much gunpowder you put in there, and also how strong the cannon is. But if you just put a little bit in and fired it, then the cannonball would go a little distance and then it would fall and hit the Earth. Okay, that's probably quite obvious. But if you put a little bit more gunpowder in and fired it, it would go a bit further before it hit the Earth. But can you see it's sort of going along and then falling towards the Earth and falling? If you put even more gunpowder in, it would go a bit further until it hit the Earth. But then if you put just the right amount in, you fire it out like this, and it would go all around the Earth, and it would never actually hit the Earth. And at this point, it would be in the orbit, in an orbit. So actually what's happening here is it's just always falling towards the Earth, but it's going so fast, it's always missing it. So it's going round around the Earth, trying to fall, but because the Earth is curved, it's always curving round, falling towards the Earth, but it's going fast enough that it never actually hits the Earth. So this is something you could do, but it is quite difficult to do. Firstly, this has to be going very, very fast. It's about 17,000 miles an hour, or 22,000 kilometers an hour, something like that, to actually get into this orbit. So that is extremely fast. That's much faster than any aircraft flies or a bullet goes. So this is why it's difficult to do in practice. And it's also very difficult to do close to the Earth because the atmosphere, the air around you slows this cannonball down. So it would eventually hit the Earth. But if you're up in space, just up in space, in the space station, then there isn't any air to slow you down, and you have a rocket that's got you there and has got you to this speed of 17,000 miles an hour. So you always go around and round. And this effect is very much like if you've ever been in a lift in a tall building and you go down, you perhaps feel your stomach move up, and you're going down quite fast, and you are actually sort of falling at this point, but you're not actually falling as fast as gravity would want you to, but you do feel slightly lighter than you would otherwise. So it's the same effect. Now you can get this on Earth, and this is some people who are doing this on Earth inside a very special airplane. So this is an airplane that flies up, goes up really quite high, and then it sort of dives down and lets everybody inside the airplane drift around as though they're continually falling, but they don't feel like they're falling. They just feel like there is no atmosphere. Now, I hope this works. I've got a small video from a TV program that shows you this happening. So I hope this. So that does look fun, doesn't it? I bet you'd all love to do something like that. I know I would. You can actually do that. You have to pay quite a lot of money, but there are a couple of companies around the world that will, you know, if you have enough spare money, they will let you fly on one of these things. It's also what astronauts do to practice for when they go into space. So they have to get used to this sort of thing. A lot of people find it really fun, and they just, as you could see, all those people were really enjoying themselves, having fun, spinning around and doing things like that. Some people find it rather upsetting, a bit like travel sickness, and sometimes they don't feel too well during that. It affects their body a little. But that is essentially what microgravity is, that you are all falling towards the Earth, but in the case of the plane, it's falling for quite a long while because it gets up really high, but then eventually it has to stop falling, otherwise you would just hit the ground, and it pulls out, and then they usually fly up again to another height and then do another one or two, and you get maybe a couple of minutes of this just falling around, doing exciting things while that's going on. But if you get much higher up into space and into orbit around the Earth, into the International Space Station, then you're effectively doing that all the time. Gravity never gets switched back on because you're just falling all the time, and you just never feel any of the effects of gravity. And I've got another video here. This is Commander Chris Hadfield, who was in the International Space Station for, I think, about 3 to 6 months, something like that. And he did some experiments, and you can see lots of things happen in microgravity that you wouldn't expect normally, because there is no up and down, and everything just floats around. If you put a pencil, if you let go of a pencil, it just stays where you put it. Well, it might spin around a little, but it doesn't fall down to the ground. It just stays wherever it is. And that is quite fun to begin with, but it can get very awkward if you're, if certain things happen. I remember one of the astronauts said he was clipping his fingernails and just clipping them with scissors, but the bits of fingernail then drift around and they float around, and other people find these bits of fingernail drifting past them. Occasionally they open a packet of sweets or something like that on the space station, and they float around, and they occasionally find these sweets days later just floating around in the air currents. Anyway, this video is of Chris Hadfield up in space, and he's looking at how this affects water.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey
microphone
puck,
just drifts around,
and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space. So instead, I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
See how the water just hovers around. It's really odd.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth And then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
So you can see really how weird things happen out in space, and there are all sorts of engineering problems you have to solve when you're working things like that. You could see him just floating there with his microphone just floating around, but what you couldn't see is his feet were wedged under a sort of a rope on the ground to keep him there. Otherwise, he would also be floating around and a bit out of control. So they use a lot of this sticky Velcro on the space station, this stuff that sticks to itself. So a lot of stuff has this Velcro on so that they can just stick it wherever they want onto whichever side of the inside of the space station they wish, just to stop things floating around. Otherwise, they just float around forever. You could perhaps see some of those little water droplets floating around, and they would just drift around, and you would occasionally run into them because they would just drift around all day. So they have to have special systems on the space station to work with that. They have little fans that draw in air and clean it so that you don't end up with things floating around forever within the space station. There are all sorts of other awkward things you might want to think. How would you take a shower on the space station? One thing that everybody always asks the astronauts is, how do you go to the toilet on the space station? That's also a tricky thing. But there are all sorts of issues, even dangers with them. There was one case of two astronauts on the space station. They went outside in their spacesuits to go and do something. They were going to attach a new instrument onto the outside of the space station. So they went out in space suits, but they have a little pouch of drinking water within their spacesuits because they maybe work for 6 or 7 hours, so they need to be able to drink. So they have a little tube that they can drink from. But in one case, one of these space suits was had a slight a problem, and it was not circulating the water correctly within the spacesuit, and it started to build up, and the astronaut could feel it on the back of his neck. He could feel this like a cold bit of water on the back of his neck, and it gradually grew and grew, and it started to, just like you saw around Chris Hadfield's hands, it started to make this sort of cover over his neck, and then it started to move around his head and face. And at this point they were quite concerned and said, well, you better get back inside, and we need to mop this up, because obviously in a spacesuit you can't get inside it to get your hands inside to help yourself out. So he had to get back inside before this became a problem and actually covered his whole head, and in which case it would made it very difficult to breathe. So that is the most common case of microgravity, is when you're falling in space and you're an astronaut out in space and you're just drifting, not under power, you don't have your engine switched on or anything like that. But they do still feel the influence of Earth's gravity. It's just that they can't notice it because they're always falling with it. If you went a really, really long distance out into space, miles away, millions of miles away from any other planet, then you would be in absolutely no gravity, or almost no gravity. So this is this case for this spaceman and his spaceship, a long way away, because as you get further and further from a planet, gravity gets less and less. Interestingly, it never really goes away. Doesn't matter how far from the planet you go, there will always be a tiny, tiny bit of gravity. Excuse me, there's an airplane just going past. But if you go far enough from a planet, then the gravity will be so tiny that really you just won't notice it at all. So if you go a really long distance from the planets and suns and everything else, then the gravity will be so tiny that at that point you really don't notice anything. So that's my quick introduction to microgravity. So what the key points really are is that the gravity gets less as you get further away from Earth, but it doesn't get less very quickly. So even those astronauts on the space station, if you work out how much gravity they would feel if they were just stationary, they would feel about 90% of it. So you would, if you weighed 100 kilograms, you would feel like you weighed 90 kilograms. So they would still feel that. But actually what's happening to those astronauts is that they're falling towards the Earth, but in a constant way. So, and they're going so fast that they always miss it. So it's as though you're just going always around and round, falling towards the Earth, but because you're going so fast, you never actually get to collide with it. And you could get the same thing by being a very, very long way away from the Earth, but and you would feel the same. So that's probably given you a quick introduction to the sense of microgravity and what it's all about. And at this point, I feel you've probably listened to me enough, and you probably want to perhaps go and do other things. But at this point, I'm going to stop sharing my screen, and we can perhaps have some questions and answers, and you could ask me questions and answers on anything, either about microgravity, space, astronomy, whatever you like. It's completely up to you. I'm quite happy to try and answer anything. If I can, I might not be able to answer it. You might be asking me too difficult questions.
Thank you very much, Dr. Julian Onions. It was very interesting. And we got a lot of students who are in need of answers for their questions. So we'll begin the question and answer session now. So first we have Binal.
Dr. Julian Onions, can microgravity affect something like a space rocket, like the TESS telescope?
Yes, well, the telescopes, so particularly the Hubble telescope, which is also in orbit, it's also going round and round the Earth. It's going around a bit higher up than the space station, so they would never crash. One is about 300 miles up, and the Hubble Space Telescope, I think, is about 500 miles up, so that they would never particularly crash. But yeah, it's not too difficult to work with that, because in microgravity, you can make things that you couldn't build on Earth, because on Earth you always have the gravity bending things around. So you can make quite flimsy things. You don't need particularly strong structures to hold them, because they will, wherever you put them, they will just stay there. So the Hubble Space Telescope, for instance, has solar panels which it uses to turn to the sun to get the sun's energy to power it, so it gets electricity, and they're on long poles. But if you tried to extend them on Earth, they would collapse and buckle and just be a complete mess. But out in space, because of this microgravity, you really don't need very much strength. You can get away with sort of just very flimsy bits of metal holding them up, because they don't really have to do very much, which is very good, because it's very expensive to put stuff up into space. It costs a lot of money. For every pound you put into space costs a lot of money. So the lighter they can make it, the better. So thank you, Binal. That was a very good question, and thank you very much for that.
Thank you, Dr. Julian.
Another question, will it affect something like so large like a cupboard?
Sorry, can you repeat that?
Will it affect something large like a planet?
So something large like a planet?
Will it affect a large thing like a planet?
Oh yeah, yes, gravity affects absolutely everything. Everything is affected by gravity. So if you're on the space station, that is quite a big thing. I think it's about I don't know, maybe less than 100 meters long, something of that sort of size. So you can drift around in that, which you can see the astronauts, but that does actually have its own gravity. So the astronauts are actually attracted to the space station because it is made of mass. It does attract it, but because gravity is so weak, it's a very, very, very tiny thing. And even just blowing like that would be stronger than the gravity of the space station. But when you get to something like a big planet, then that has much more to it, so it starts to get a bigger gravity. So there are some tiny planets, what we call dwarf planets, usually. So in the asteroid belt, there is a planet called Ceres, another one called Vesta, and they are not particularly big. They're about maybe 100 kilometers across, something like that. So much, much smaller than the Earth. And they do have gravity, but not very much. So if you stood on Vesta, for instance, in a spacesuit, because there is no atmosphere, you could jump really very high. In fact, it would be quite dangerous. If you jumped really hard on Vesta, you would keep going up and you would be going faster than the gravity of Vesta. So you would disappear and no longer be part of it. You would just drift off into space. You can't do that on the Earth. I bet you've tried. No matter how high you jump on the Earth, you're always going to come back to the Earth. But on Vesta, it's the gravity is light enough that you can jump up and leave the Earth forever, leave Vesta forever. So you would have to be very careful if you lived on Vesta to make sure you didn't do that.
I have one more question. What will happen to the Earth if gravity disappears?
What would happen on Earth if gravity disappeared? Yeah, that would, well, we would all just float away, and everything would float away. Everything not stuck down, not actually attached to the Earth, would just float around, and we would just drift around. It would be quite catastrophic. All the water in the oceans would sort of just drift around and float around, and it would be a complete mess. But luckily, we don't know how to do that. We don't know how to switch the Earth's gravity off. As far as we know, there is no way to do that. So we're going to be safe. But it's interesting to think about that question. So thank you for that question.
All right. Thank you, Dr. Julian.
Thank you.
Yes. Next, we have Imalka.
How close do a black hole need to be to do a tiny effect on a planet?
Oh, that's a good question. So black holes, just like planets and the sun, they all have gravity. Black holes are a bit extreme in that they have all their mass packed into a very, very tiny place. So they have gravity just like anything else. And they are almost like a planet or a star or anything else like that you could think of. So if you took a spacecraft to a black hole, you could go into orbit around it, and you could go around and around it, and you wouldn't feel anything particularly different about that. It would be just like being in a space station around the Earth. The danger with a black hole is there is a place around the black hole, well, all around the black hole, that if you go past that, you can never come back. So if you are in a big orbit around the black hole, you're fine, and you just drift around like the astronauts on the space station. You wouldn't know particularly that there was anything odd going on. But if you then went on a smaller orbit, got close to the black hole, you'd go around a bit quicker. And then at some point, it's called the event horizon. If you crossed that horizon, then you would get sucked into the black hole and never be able to come out. No matter how powerful a rocket or spaceship you had, there is just no way you could come out of that black hole. It's excuse me, it's the same with the Earth to an extent. If you get close to the Earth, like we are now, we can't escape from the Earth by jumping. It doesn't matter how strong your legs are, they are just not strong enough to escape from the Earth. But if you get something much stronger than that, like a very powerful rocket, you can escape from the Earth. The difference with the black hole is there is no rocket you could build that is strong enough to escape from it once you are past this closest point. So thank you for that.
And another one.
Yes, Simanka, you may ask.
What will happen if the sun be a black hole?
What would happen if the sun became a black hole? If the sun became a black hole, we wouldn't really notice as far as the Earth is. Well, we would notice, but the Earth would still carry on going round in its orbit. So you would still have the year, you'd still have birthdays every year, and it would keep going round and round because the gravity would still be there, and that would keep the Earth in its orbit. The difference would be we would have no sunlight, and that's something we can't really deal without at the moment. We do need the sunlight to live. We need it to grow the food. We need it to warm the planet and all that sort of thing. So if it turned into a black hole, we wouldn't, there wouldn't be a danger to the Earth as such, but the Earth wouldn't be sucked into it because we would be far, far too far away from the black hole to be in danger of that. But we would suffer in other ways because we would no longer have the sunlight to keep us going. So yeah, thank you for that. That's a very good question.
All right. Thank you, Dr. Julian. Next, we have Nevan.
Excuse me, Dr. Julian, can you remember you gave an equation, you gave a physics equation that's F equal to GM1 M and R2. What's the meaning of that equation?
That just tells you if you have all the numbers, you can work out how much the force of gravity is. So if you know how much the two things you're looking at, say yourself and the Earth, how much they weigh, and how far apart you are, you can tell how strong gravity is. So that doesn't really mean very much to you walking around on the Earth because you know how strong gravity is. You can just feel it. You know you're being held down to the Earth by this force. But it is important for people like rocket scientists and space explorers because it changes. So when you get to the moon, you are now on a body with less mass. So before they flew the Apollo astronauts to the moon, they had to try and work out, using that equation, how heavy would the astronauts feel they were? How much weight could they lift? How much could you put on their backs for oxygen and heating so that they could live? And they could use that equation to work that out and say, well, they can lift about 6 times as much on the moon as they can on the Earth. So using that equation from Isaac Newton, they could work that out. So they knew that when they got to the moon, the backpacks they put onto the spacesuits would not be too heavy for the astronauts to lift. They could be well within the ability to lift. Back on the Earth, they would weigh quite a lot. I think they weighed about maybe 100 pounds or something like that. So that's quite a lot of weight to carry around, and you would get tired very, very quickly on the Earth carrying that around. But because on the moon it weighed a sixth of that at about 15 pounds or something like that, it was quite easy for them to walk around all day carrying this sort of heavy weight on their backs because they didn't have nearly as much weight. And they had to work that out before they got to the moon, because it was no good getting to the moon and saying, well, can you lift that up? Because they couldn't come back from the moon and say, well, let's have a smaller pack. They had to work that out beforehand. So that is why they needed this equation to sort that out. Yeah, it's a very good question.
Thank you so much, Dr. Julian.
All right. Thank you, Dr. Julian. Next, we have Ayusha.
Excuse me, Dr. Julian, how much mass does the sun have?
Sun has it's a huge amount. So it's if you wrote it down in kilograms, you would write a number 2, and then you would write 30 zeros after it. So that's something you could try and write, 2 and then 0, 0, 0, 0, 0, 30 of those zeros. So it's really, really heavy. It's quite crazy how heavy it is. You could do the same with the Earth, but in that case, you would write, I can't remember the number for the Earth, but it would be something like 1 with 24 zeros after it. And the Sun is 2 with 30 zeros after it. So you could try writing that out on a piece of paper after this and just see how big it is. But when numbers get to that big, it's just your mind really can't cope with how big they are. You can't really compare how big this is with something else. It's a very difficult thing to get into your mind, exactly how heavy that is. But they are staggeringly big.
Another one, Dr. Julian, what is the difference between gravity and microgravity?
So, well, there isn't really any difference between the two as a sort of a physical thing, but it's just the effect they have on your body. So gravity, you feel yourself being pulled down to the earth, and there is an up and a down. You know that you lift your arm up and it falls down. In microgravity, nothing falls. Everything is wherever you last put it, that's where it will stay. So it's a very weird and interesting place to be in, and you have to think a lot about exactly how you're going to live in that. So you can't just have a plate of food, for instance, because if you put all your peas on the plate or your or peppers or whatever else on the plate, they would just start drifting around all over the place. So they can't sit down and have a plate of food and eat, because the microgravity just means that it drifts around wherever it goes. And everybody would get very annoyed with you on the space station because all your food would be coming past them, and it would be doing that for days. So instead, they tend to put it in little pouches and have a straw to drink it from, so that it goes from the pouch into your mouth without affecting everybody else. So yeah, it's a very weird and interesting place to work in. I would love to go there one day, but not many people get to go to space, and I don't think I'm ever going to get to go to space. But some of you could well do if you study and become part of NASA or one of the other space agencies. There's quite a lot of space agencies these days. Then maybe you'll get to go to space. If you do send me a postcard.
Thank you very much, Dr. Julian Onions. Next, we have Sudhita.
What powers quasars?
Sorry, I didn't catch that. What purpose? Could you repeat the question?
Quasars?
I still didn't catch that.
What powers quasars?
Well, what powers quasars? Oh, right. Oh, wow. That is a very, very good question, and one that we've only been able to answer in, I guess, the last 20 years or something like that. So that's something a lot of astronomers have tried to work out. So quasars are very, very powerful objects. They are some of the most powerful objects in the known universe. They are extraordinarily strong objects, putting out a lot of energy. And they are actually a giant, well, what we worked out, or our best guess of it, or our best idea, is that they are a huge black hole at the center of a large galaxy, and it's something that weighs an enormous amount. So when we get to measuring things in galaxies and planets, we usually use how much does the sun weigh. And I said the sun weighs a 2 with 30 zeros after it kilograms. So because that's such a big number, we don't usually use that number. We instead say it weighs as much as a sun. So we work in how much it weighs in terms of a sun. So these big black holes at the center of galaxies, they weigh about 4 million times the weight of the sun. And some of them weigh even more. Some of them weigh 4 billion or a billion times the weight of the sun. So they are huge, enormous things. And they last as quasars for many years. certainly millions of years, and some cases billions of years. And it is this big black hole right at the center of the galaxy that is powering that. And they are so strong, the amount of energy they're putting out is so amazing that it's really difficult to comprehend. But if we took the Earth and we moved it out to where Pluto is, so Pluto is a long, long way out from the sun. It's 40 times as far from the sun as the Earth is. So if we took the Earth and moved it 40 times away and put it in orbit around the sun, and we changed the sun to a quasar, and we were orbiting that quasar would have enough energy to boil all the oceans on the Earth into steam in half a second. So you can imagine what would happen to the rest of us. There would be so much energy coming out of that. Everything would just turn into vapor very, very quickly. So we wouldn't want to be anywhere near a quasar, and luckily we're not. We do have a black hole at the center of our galaxy, but it is not in a what we call a quasar mode. So it is just sitting there not doing very much. If it did turn into a quasar, that would be quite dangerous for us. But luckily it is not. That's a very good question. Thank you.
Thank you, Dr. Julian. Next,
I have one more question.
All right.
What will it be like if the Earth was inside a nebula?
Inside a nebula? Oh, that's interesting. It would be kind of interesting, I guess, in that nebulas, if they've got stars in them, they tend to glow a little. So we would perhaps look up at the night sky and it might be glowing a little in the reddish, but nebulas are very, they're big clouds of gas, but the gas is very, very thinly spread. So there is a lot of gas in a nebula, but it's spread out very, very thinly. So if the nebula was, say, made out of oxygen, it would be far too thin to breathe. There would just be a few atoms here and there scattered around. So they are very, very large objects, and they span a great distance, but they are made up of a very thin amount of gas. So you might well see a little sort of reddish color if we lived in one, but other than that, you wouldn't notice very much. If you went out into space, you wouldn't really feel the nebula because it would be so thinly spread that it just wouldn't be any difference almost to the vacuum of space. Good question.
I have another question to ask. What will happen after the big crunch?
Big crunch. Oh, that's the end of the universe, that is. These days, we don't think the big crunch will happen. So we used to think the big crunch would happen. The universe expands out like this, and we used to think gravity will slow it down and pull it back in, and we'll have a big crunch. But since those days, which was about 30 or 40 years ago, we've worked out some other things, and there are some other forces, and actually the universe is just going to go expanding forever. So we're not going to have a big crunch. We're just going to go get bigger and bigger and bigger.
Okay, my last question is what will happen if we try to go at the speed of light, because electrons are when they are getting faster, they are getting heavier. So what will happen?
Yeah, that's a very good question, and one we don't really know the answer to. We know we can't go at the speed of light because that wouldn't work. As you say, things would just get far too heavy. We can get close to the speed of light. We can do it with very light things like atoms or electrons, but we can't get them to the speed of light because they just get heavier and heavier as you try and make them go faster and faster. And eventually, all the energy you're putting into trying to make them go faster makes them just get heavier. So we can't get them to go any faster. So yeah, very good question, and one that we don't really know the answer to at this point. So perhaps you can answer it for us when you've done some research and become a physicist.
Thank you, Dr. Julian. Kids who have questions, please make sure that you all base your questions on today's topic because we are running out of time. Right. So
Yes,
we got
fair enough.
Osit, got any questions?
Excuse me, sir.
Yes. What is in the other side of a black hole?
That's yeah, that's an interesting question. So there isn't really very much on the other side. If you went into a black hole, you would just disappear. That you would never be able to come out and tell us what you found. If you went around a black hole, it would be just like going around a planet or a star. You would just go round to the other side, and it would be much the same. So you could go round and round the black hole forever, as long as you didn't get too close. But the same is true of the sun. You could go round and round the sun forever, but if you get too close, you would melt. So it's a bit like that with a black hole.
All right. Thank you, Dr. Julian. Next, we have Arudit.
What if
Yes, Arudit. Hello.
is the gravity from a quasar stronger than the gravity from a black hole?
Is quasars more powerful than the black hole? Is that your question? In which case, they sort of are and they sort of aren't. Quasars are powered by things falling into the black hole, but once they've fallen into the black hole, we would never see them again. So that isn't actually what's happening. What we are seeing is the stuff that is falling in, and it's going around and around the black hole, getting very, very hot as it's spiraling in. It's a bit like if you have a big bath and you pull the plug out, you see the water going round and round and round, and then it disappears down the black hole, down the plug hole. It's that effect of the water going round and round just before it goes down that we're seeing. That's kind of what we're seeing in the quasar.
Thank you, Dr. Julian. So we got Ryan, Thyssen. Guys, got any question? Anaya? No questions? Right. All right. I think that's it.
I have one question.
Yeah. Oh, yeah. You may ask. Yes, Simal.
How fast is the quasar?
Quasar isn't very fast in itself. It's just sitting there. The black hole that is powering it is just sitting there. But the energy coming out is very, very fast. It's almost the speed of light. It's coming out at an enormous rate and is, as I say, really, really powerful. So the energy coming out of it is coming out extremely fast. Some of the strongest things we know in the universe. So yeah, don't get too close to a quasar would be my advice. It would be not good for you.
I also have a question.
Am I a fan of?
Yes, Sudhita.
And what happens if the moon disappears?
If the moon disappears, not too much, I don't think. We wouldn't have the same tides that we have at the moment. So this sort of a high and low tide that you see on the coast, you wouldn't get quite as much of that. We wouldn't get the light at night. So that would be good for astronomers because the moonlight makes it difficult to do telescope observations. But I think we would be much poorer because it would be something that we've grown used to and we would no longer see it. So yeah, I think it would be a shame if we lost the moon. It's also a very easy, relatively easy place to get to. So we have had astronauts get to the moon. Everything else is really hard to get to. So Mars is much, much further away, and Venus is a very nasty place to go to. So the moon is a much easier place to stop off at than anything else.
Excuse me, Dr. Julian. what they say that the sun reflects the moon. No? If the moon disappeared, what would the sun reflect?
Well, it would just not hit the moon anymore, and it would reflect off other planets. But otherwise, it wouldn't really make very much difference. The sunlight would just go out until it hits something. So yeah, we wouldn't get nearly as much light at night. When you get a full moon, you can see quite well to walk and so on, but you don't get very much light from the stars. So that would be a bit of an issue, I guess.
Okay, Dr. Julian,
And Dr.
thank you very
Julian,
much.
I have
Excuse me.
another question to ask.
Okay, I've probably got time for one more question if anybody's got one.
Yes, Dr. Julian, I have another question.
Kids, Dr. Julian Onions has other appointments to attend, so we really don't have much time. So it's better we wrap up today's session. Yeah. So I think everyone was given a chance to ask questions, right? So thank you very much, Dr. Julian Onions. We'll definitely have another session as well in the upcoming weeks, because as you can see, there are a lot of questions from all of these kids. So unfortunately, today we have to wrap up today's session due to other reasons. So thank you very much for joining today's session, Dr. Julian Onions. It was really interesting, very informative, and I really hope to see you again in the upcoming sessions as well. Thank you very much.
I hope so too. Thank you very much for your questions. They've been very good.
Bye, Dr. Julian.
Have a nice day,
Bye,
Dr.
Dr. Julian.
Bye,
Thank you
everybody.
so much.
Have a good day.
Dr. Julian.
Bye, sir. Bye, sir.
Julian.
Hi, sir.
Good afternoon, sir. Bye, sir.
Bye.
All right, kids, please make sure you don't leave the session. Guys,